So our next speaker, and once again, apologies to those who joined a bit later. So we had some reshuffling of the timetable. Janusz Pętkowski will not be speaking today because of unforeseen circumstances, and things got shifted a bit because of technical issues, but we are still on track. So our next speaker is Giuseppe Cassone, and Giuseppe will talk about actually a work that is more related to simulations, just as Jacobo talked. It will be a bit more from first principles, from the point of view of quantum chemistry. And Giuseppe is a researcher at the Institute for Chemical and Physical Processes. So that's National Research Council of Italy. If I remember correctly, it's Messina, is it, Giuseppe?
Yes, that's correct. Are you able to hear me and watch my screen?
Yes, we see your screen. We hear you very well. So wonderful. Take it away, Giuseppe.
Okay. To thank you, Rafal, but also all the organizers for this nice opportunity you are giving me for presenting some of the research that we perform here at the Institute for Chemical Physical Processes in Sicily. And today I'd like to talk with you about some advanced computational approaches that we usually employ for astrochemical problems and processes. And as you may be aware, there exists a plethora of computer simulations which are able to be applied for very different systems and for very different problems. But when you need to describe the behavior of matter for astrochemical reasons, so when chemistry plays a key role, you need to go to the atomistic and molecular length scale, either if you are interested in gas phase chemistry or in condensed phase chemistry, you need to recover and the quantum mechanical and density functional theory laws. That's what
Giuseppe?
we do in particular. Yes?
Can you make it full screen for us?
Yeah, it's not full screen.
We just see your, we like see the thumbnails on the left. And
okay, so,
PowerPoint
okay,
window.
Just a moment. Let's see.
You can share the whole screen, not
yes,
just the application.
Probably this way it's better.
Excellent.
Okay, so great. So we basically employed the laws of quantum mechanics in the density functional theory fashion in order to perform ab initio molecular dynamics to mimic the behavior of matter at the best of our possibilities by exploiting supercomputing resources. So why these kind of methods, which are called ab initio methods, since they solve the electronic problem from first principles, is needed? Well, it is needed because when chemistry plays the pivotal role in the behavior of what you are simulating, you need to solve the Schrödinger equation associated with the Hamiltonian that you can see here, and where all the electron and electron nuclei interactions are taken into account. However, if you try to solve it in the standard fashion, you will fail for sure, because the computational demand is too high, and you need to recover the density functional theory within the Kohn-Sham scheme, where a many-body electron problem is mapped into a single particle problem. So this way it becomes implementable in supercomputing algorithms. All these equations, maybe if someone is interested, we can talk about them more in detail later. But these equations translate in the possibility of watching and investigating and sometimes manipulating electron densities, so atoms, molecules in gas and condensed phase. And all of these kind of simulations can be performed under dynamical conditions and by explicitly including the external conditions, such as, for example, pressure or lightnings or temperature and so on and so forth, or combination of them. Some years ago, by exploiting similar kind of simulations, the group of Neil Goldman at the Lawrence Livermore National Laboratories in the US, for the first time was able to simulate with the tight binding density functional theory molecular dynamics, which is an approximation of density functional theory, was able to simulate the effects induced by very violent shock events on an interstellar ice or a cometary ice prototype. In practice, they built a simulation box that you can see in this slide, which was composed by methanol, water, carbon monoxide, carbon dioxide, and ammonia molecules, and subjected to shock waves propagating at velocities of about 9-10 kilometers per second. So the simulation box under these conditions is squeezed, is compressed, and the transient formation of polymers was detected. But the real interesting point of this investigation was that after the decompression process and the quenching of the simulation box, they were able to identify some glycine containing polymers, and this result was obtained independently of any guess on the composition of the atmosphere, of the impact between the model cometary prototype and the planet on which he was simulated the collision. So after some years after this pioneering investigation, we asked ourselves, in collaboration with the Italian National Astrophysical Institute, we asked whether a very simple system just composed of the most abundant molecule in the universe, so molecular hydrogen, and the simplest molecule containing the 4 biogenic elements, which is asparagine, acid, HNCO, whether this system were able to give to an interesting chemistry by solving the laws of quantum mechanics in ab initio molecular dynamics simulations coupled with a multi-scale shock compression technique. So basically, we repeated the same experiment with a lower number of approximations from the quantum mechanical perspective. And when our simulation box was subjected to progressively increasing velocities of the shock impact, we noticed that, as you can see here, from the hydrogen to hydrogen spatial correlations, that whether the black curve that you can see on the screen is characterized and corresponds to the steady state where no shock compression is applied on the simulation box, a lot of molecular hydrogen molecules are present. As you can see, the first peak is located at around 0.76 angstrom, which corresponds to the typical length of the hydrogen to hydrogen covalent bond. By increasing the velocity of the shock and hence the peak pressure reached in the system, a lot of hydrogen is consumed and is converted in something else from the chemical perspective. So if you give a look at the carbon-to-carbon correlations, you see that when no shock pressure is applied to this very simple system, no carbon-to-carbon bonds are, of course, present. At the highest speed velocity simulated, which corresponds to 10 kilometers per second, and which can be interesting for grain-to-grain collisions, for example, for this kind of molecules encapsulated in interstellar or interplanetary ices. A net sharp first peak appears and falling at a distance of about 1.5 angstrom. So this is the signature of the onset of some of new carbon-to-carbon bonded species, and in particular, by inspection of the trajectories, we identified the presence of ethanimine, which is the direct precursor of alanine, the onset of glycine, but also the onset of vinylamine, which is the precursor of 7 over the 20 amino acids composing life as we know it. So this kind of work has several implications. The first one is that, as you can see here, the reach inventory of chemical of molecules which have been synthesized only by shocking a very simple system composite of a bunch of molecules of HNCO and molecular hydrogen molecules. And another finding was the role played by a key molecule here, which is formamide, which was the first molecule synthesized, spontaneously synthesized in the system at a speed velocity of about 7 km per second. And the strength of these kinds of simulations is that you're able to directly watch the mechanistic pathway followed by chemical reactions in the system. Here you see the direct hydrogenation of isocyanic acid to form formamide. And here, these are some snapshots with the relevant time scales for the formation of glycine in the system. The important stuff is that glycine and all the remainder species were observed after the decompression process, so after the reaching of the equilibrium of the system. Of course, not just impacts, as I said before, but also these kind of techniques, of simulation techniques, are capable to reproduce, for example, lightning events. In particular, we have some collaborations, an important collaboration with a group based in Prague at the Czech Academy of Sciences, where they have access to some facilities where they are able to reproduce both collisions, violent collisions that we talked about just before, but also lightnings, so laser plasma at very high power. The problem that experimentalists in the lab generally have is that they know the reactants, they know the products, but they do not know anything about the chemical pathway connecting reactants and products. So what generally computational scientists do is to employ this kind of techniques, which are traditional quantum chemical techniques, where you, by your end, build up a likely chemical pathway driven by your own chemical insight, but at the end you create it by your end. And even though you have a very realistic picture from the electronic perspective, you sometimes lose something from the entropic standpoint. So what is possible to do nowadays is to couple ab initio molecular dynamics techniques, or whatever molecular dynamics techniques, with a technique known as metadynamics. This kind of technique is capable to reproduce a given chemical reaction only by knowing reactants and products. Here you are watching an example for the dehydration of formamide to form water and HCN. And the strength of this kind of simulation is that at the same time you reconstruct the underlying free energy landscape by by letting the system probing the configurational space, or better, the collective variable space.
About 2 to 3 minutes.
Yes. So recently we applied this kind of new methods by combining ab initio MD and metadynamics to some simple chemical reactions, which can in principle occur in the interstellar medium or in interplanetary medium, with the aim of exploring the chemical contribution offered by, for example, interstellar ice to some chemistry. For example, here you can see the conversion of HNCO and methane into methyl isocyanate and molecular hydrogen, which is hindered by a very high free energy barrier of about 140 kcal per mole. But if you put your reactants within a matrix of amorphous water ice, this barrier is lowered to 46 kcal per mole. And if instead of pure amorphous water ice, you employ a matrix of water, 50-50 mixture of water and carbon monoxide amorphous ice, this free energy barrier is lowered to 35 kcal per mole. These kind of calculations treat explicitly and exactly all thermal and entropic contributions, giving so better guess generally to the free energy of the estimate of your reactions, and by treating at the same level, at the same quantum mechanical level, the environment directly gives you a better glance of what is going on in condensed phase systems. So definitely interstellar ices not only are capable to gather and accumulate interesting or molecules, but also to increase the kinetic rate of this kind of reactions of several orders of magnitude. And these are some of our co-workers that I would like to acknowledge. And of course, I'd like to thank you for your kind attention.
Thank you very much, Giuseppe. Very interesting talk. So what you showed are these very interesting reactions which happen in, for example, condensed phase or gas phase. But you simulate many molecules, which is also a very nice achievement with methods of quantum chemistry. But can you also take into account surfaces that could simulate, in a way, the dust grains? And have you ever tried it? What are the possible challenges with it?
Okay, thank you, Rafael, for this nice question. The answer is not. I didn't. However, it is of course quite feasible. I mean, many research groups already started some simulations on it, and the real strength of this kind of techniques is the possibility really to be creative in building up your simulation box, so you can put liquids in contact with solids, or a gas phase reaction occurring on surfaces like those that you mentioned. So it's quite straightforward to extend this kind of simulations also to this to heterogeneous catalysis or similar chemistry or similar systems. So it's definitely possible.
Mm-hmm. Very interesting. I mean, and another question that comes here. So you showed how these reactions can lead to the formation of amino acids and amino acid precursors. How about some precursors of nucleic acids, so DNA and RNA? Do you also see them in your reaction mixtures?
So in our, I will just reach very rapidly in our simulation here, for example, it was just a sort of proof of concept simulation where we just put the two of the simplest molecules we know that are present and somehow abundant in the universe. And no, in this kind of simulation, no, but this is this can be. This is due likely to the limited size of the simulated box, because we had just 32 molecules of isocyanic acid and 50 hydrogen molecules. So probably with bigger, larger simulation boxes, or by including some other reactive molecules, for example, water, for example, ammonia, and so on and so forth, by creating their own counter ions upon shock, likely an even more multifaceted and complex chemistry can definitely occur.
Thank you so much.